All right, let's go ahead and get started again. Fortunately, this is just kind of one of those things that you need to mull over, do some examples to make sure you're feeling comfortable with it. What I've got planned for the rest of the class is just to go through maybe a fourth of your homework and just practice it that way. It's not terribly complicated. It's not any more complicated than what we went over the first half of the class, but you just need a chance to practice it. And while I've got you here, I'm going to stay here another hour or so and just try to make sure you understand it. So with that, let's start with a couple of these problems. Let's start with page 316. Let's look at question number 2. All right, let me go ahead and read it to you, and we'll think about how we would set up this hypothesis test. So, question asked, average delivery time for orders shipped by Manatee Printing to customers in Europe is 6.5 days. Now, you plan to try a new shipping service that promises to reduce that time. You intend to select a random sample of orders to be delivered by the company and use results from the sample in a hypothesis test designed to establish whether switching companies will have the desired effect. What null and alternative hypothesis would you recommend for the test? So, you've got an average delivery time for your current business model of 6.5 days, and you're looking at a new shipping company, and you want to know if statistically you can determine that there is an advantage to switching to this new company. So your job is to think about what you would do for a null and alternative hypothesis to establish your best plan of action. So, we're going to need a null hypothesis, and we're going to need an alternative hypothesis. I'll give you a hint. 6.5 is going to be critical in both the null and alternative hypothesis. Amanda, shed some light on it for us.
It will equal, less than 6.5.
Which one? The null or the alternative?
The null.
The null, okay. What do we got?
It'll be, how do you word it?
So the mean, so we're looking at, all right, average.
Will be less than 6.5.
Okay. Well, let's think about what we're potentially trying to prove. We're trying to prove that this new shipping company has a faster shipping time.
Okay. So it would still be less than 6.5 days.
Yeah.
You want to make
But we want that as the alternative hypothesis. Because we want to find overwhelming evidence that the new company is faster. So, that's going to be the alternative hypothesis, that the mean is going to be less than 6.5. We want to know if we can be confident in our decision to ship with this new company. And the alternative hypothesis is going to be the opposite of that. The mean is going to be greater than or equal to 6.5. So here we are. We've got a shipping company that we're using that takes an average of 6.5 days to ship. And we're going to sample this new company to see if they can get less. So we need significant proof that this new company is faster. And so we're going to call that significant proof the alternative hypothesis. So the null hypothesis, this shipping with the new company, is greater than or equal to the 6.5 that we have now. So we're going to take some samples, and we're going to we're going to find a sample mean. Suppose we come up with a sample mean of 6.7 days. What do we think about this at this point? We have this new company that had an average shipping speed of 6.7 days. Do we like them?
No.
No, we don't like them. They're higher than our current.
Yeah.
All right, so we don't like them because it came out higher. So not only do we not like them because it's higher, but we certainly don't have overwhelming proof that they're faster. Now, what if it came out to sample mean of 6.3? How do we like that? Well, we definitely like it better. So now the question is, do we have overwhelming proof to reject the null hypothesis that this company is just the same as the old company and assume that they actually have a statistically significant faster shipping speed? Does that make sense? And we need some more data to figure that out. But all we're asked to do in this question is to set up the null and the alternative hypothesis. All right, I think it's important to think this through. Can someone summarize that back for us, just so we get a chance to just process that? Everyone, including myself. Yes, Phil.
They want to create a new system or whatever is going on to be able to ship their product less than 6.5 days. So in order to prove that, they want to be able to reject that it would ship over the 6.5 days.
Yeah, they want to
And
reject
by rejecting
Right.
that it's greater, you can.
that it's the same or slower.
Right.
Is that our null hypothesis is that this new company is the same or slower. So we certainly need evidence that at least it's a little faster. So we need at least something below 6.5. And then is it going to be based on our significance level, proof enough to justify switching companies? Yes, Nadia.
So in general, you want to always discount the null hypothesis?
Well, typically the alternative is what we're looking to prove. So you tell me that the rent is higher. I think the rent's higher than that. I'm going to set up a hypothesis test where I can prove that with the alternative. That's where there's going to be a burden of proof, is rejecting the null and accepting the alternative hypothesis. Make sense? All right, great. Let's move on to number 6. And this involves some calculations, I believe. Let me give you a chance to just work it out. Yeah, let's do that. Does everyone have? Can everyone have number 6? Hey, Justin, you can make a friend. All right, let me give you page 322, number 6. Just think about how you're going to approach that problem, and we'll come back together as a class. right, let's go ahead and come back together, unless you need a couple more minutes. Are you ready to come back together? Everyone's head is down, so I'll take that to mean 1 more minute. I can read body language. All right, let's go ahead and come back together. In this problem, we've set up an alternative hypothesis that the mean is less than 2,000. Maybe we're testing how many miles a tire will last, and we have a suspicion, we have a concern that maybe they won't last the full 2,000 that our supplier says they'll last. But we're going to give the supplier the benefit of the doubt and say that the mean is greater than or equal to 2,000. And we're going to set up an alternative hypothesis that the mean is actually less than that. And if we find overwhelming evidence that it is, then we are going to reject the null and say, gosh, it really is less than 2,000. We take a sample of 100 whatevers. We come up with a sample mean of 1950. We know that the standard deviation for the population is 150, and we want to run this test at the 1% significance level. So we have a very rigorous standard of proof. So we know if we were to put all these sample means on a distribution, it would come out to be normally distributed. Assuming that what the supplier tells us is true, the mean is 2,000. Okay? And we calculated a sample mean of 1950. 1955, excuse me. So we calculated a mean that was less than 2,000. So there's a possibility it may be enough less to disprove the null and give us something substantial that we can say about this. Next thing we need is our critical values. All right? How much less than 2,000 in terms of z-scores is going to get us to say that's too extreme. That's too unlikely. I'm going to reject the null. So let's see, critical value. Critical value. What did we come up with in terms of critical values? How much? First of all, is it a positive or a negative z value? Negative. All right, so it's going to be a negative z value. It's going to be below the mean of 2,000, which means it's going to have a negative z-score. What is that value? So we're looking for the point at which 1% of the data is below that z-score, and 99% of the data is above that z-score. So I'll do the hard part here. I'll put negative. You do the easy part and tell me the rest. Negative, Diana? 2.37 sounds right. 0.37. Anyone? Let me check. Believe it or not, I actually did the homework myself. So I got negative 2.33, but I don't know. We'll go with Diana's negative 2.37. Sounds good enough for me. So our next step is to calculate this z statistic. Is this sample mean, we know it's below 2,000, but is it far enough below 2,000 to have a z-score of negative 2.37 or lower, such that it would give us cause to reject the null hypothesis? So let's calculate it. So we take the sample mean, 1955 minus 2,000, divided by the standard deviation of the sampling distribution of the sample means. And we know that the standard deviation is the 150, the population standard deviation, divided by the square root of n, which is the square root of 100. I like how these problems, the authors make it easy for you. They put the sample sizes into easy square root variables. Did anyone get this far?
Negative
3? 0.3?
No, negative 3.
Just negative 3.
Yeah.
Okay. What did I get? Negative 3. Yes, that's what I got. I got negative 3. Okay, so we have everything we need to know to calculate.
Reject.
Reject. Outstanding. Reject. Reject the null hypothesis. So we go to that supplier that told us their tires lasted 2,000 miles. We're like, not so much. Make sense? Great. Let's move on. Let's do number 22, which is going to be on page 328. Page 328, 22. It also looks like it's again a one-tailed test. We want to calculate the p-value, which means basically we're going to do the same thing we did, except that extra step of calculating the p-value. So go ahead and see if you can crunch through number 22, page 328, and then we'll come back together in 4 minutes. All right, let's do it. Let's come back together. So, we've set up a hypothesis test where we might want to prove that the mean is less than 500. Suppose some company tells us that they can do 500 downloads a minute. And we're like, yeah, I think that's a little bit on the ambitious side. I'm not sure you're performing quite that. But I'm going to set up a hypothesis where I'll say you're doing that or even better, and I'm going to assume that's true. And I'm going to collect some sample data and see if it warrants proving that you download less, significantly less than 500. We know the standard we take a sample of 81, download sessions, whatever. We get a sample mean of 488 downloads per minute, and we have a standard deviation of 36. So, are we looking at a one-tailed or two-tailed test? One-tailed. Because we're only concerned with the one side. Now, we put everything on our sampling distribution, the sample mean. I should actually write that. Sampling distribution of sample mean. All right. We know the mean, assuming what they tell us is true, the mean is 500. All right, we've got a sample mean x bar of 488. And our, I forgot to put critical value.
Yes.
Our significance level is what, 1%, right? 0.01? Is that what we're looking for? Oh, no, we're trying to find p-value. All right, we're trying to find p-value. So we're going to set it up the same way. But the first thing we want to do is just find the z statistic. So, z stat, all right, is going to be our 488 minus our 500 divided by our standard deviation of the sampling distribution of the sample mean, which is 4. 4, okay. 4, because we know the standard deviation is 36, the sample size is 8, so standard deviation, sampling distribution, sample mean, equals 36 divided by the square root of 81 equals 6 divided by 9, which equals 4. All right, and we can do it in our head, right? Yeah, so this is negative 12 divided by 4 is negative 3. Okay, so we've calculated a z-score, not a critical value. Our critical value is our decision point. A z-score of negative 3. All right, so that is on the extreme edge of the left-hand side of the frequency distribution of the sampling distribution of the sample mean. Question is, what are the chances of getting something that extreme or more extreme? And we answer that question by determining how much of the data is below negative 3 on the z-score. So we crack open our z table, and we get a p-value. And what do we come up with when we look at negative 3 on the z-score? All right, America? 0.0013 or 0.13%. So pretty much 1/10 of 1% is how much data is more extreme than that. So there is a 1/10 of 1% chance that this just happened randomly, assuming what the developer told us is true. Assuming that the mean really is 500, well then there's a 1/10 of 1% chance that we would have come up with this. No. Not quite. We're going to say at the both 1% significance or 10% significance level and at the 5% significance level, what do? Reject or fail to reject? We reject.
Reject. Yeah.
Reject. Because this is so unlikely. 1/10 of 1% at the 10% level and at the 5% significant level, we reject. Any questions on that? All right, we'll keep it moving here. So next, I would like you to take a look at page number 32, which is on page 335. Number 32, page 335. let's come back together. Let's talk this one through. How have we set up the hypothesis test? Someone give me the basics on that. So we're assuming the mean, whatever it is 1,000. And we're looking for contrary evidence to prove overwhelmingly what?
That's not exactly 1,000.
That that's not exactly 1,000. And what are the ways in which we might prove that it's not 1,000? There are two.
That's nice.
It could be really, really high, right? And we say that's way too unlikely for it to be that high, given that if the mean is 1,000. Or it could be really, really low. And we say no, the sample mean would not be that low if what you say is true. So is this a one-tailed or two-tailed test? Two-tailed test. So we're concerned about a really, really high possibility, really, really low possibility. If we get either of those, we say, all right, well, granted, there is a chance of it being there, but that's so unlikely I'm going to reject your hypothesis that the mean is 1,000. The instructions on this say go straight to the z statistic, and we have the information we need to calculate it. So let's do it. So we've got a sample mean of 975. 975 minus the mean that we're assuming is true. This person who we may be skeptical about, who looks a little shady, told us it's 1,000, but let's just see what happens when we crank that out. Divided by the standard deviation of the sampling distribution of the sample mean, and that's going to be the population mean of 90 divided by the square root of 81. All right, what do we get when we crank that out?
Negative 2.5.
Negative 2.5. Okay, now we're looking at a z-score somewhere in here. We don't know quite yet if it's in the critical region because we haven't really discussed that, but we know it's fairly extremely negative. The question is it negative enough given the way that we've set up this test? And what they're asking us for, first let's calculate the p-value. All right, so what is the p-value of a test statistic, a z-stat of negative 2.5? The first thing we do to calculate that is we look on our z-table and say, well, negative 2.5, how much of the data is below that? How much? All right, 0.0062. That sounds right to me. So, question I need to ask you, though, is that the p-value, or is there something else we need to consider? Multiply it by 2. Because there is, so this 0.0062, which is, or, what is that, 0.62%? Right? Is that right? Yeah, so there's about 1/2 of 1% chance of getting something that low. But we could have also gotten something really, really high, in which case we would have rejected the null hypothesis as well. Two-tailed test. There are one of two ways we could disprove the null hypothesis. It could be really, really low, or it could be really, really high. So we multiply that by 2. Because either case, if it had landed here or landed here, we would have said, whoa, that's way too unlikely. So we multiply that by 2 and we get what? 1.24%. Okay, so that's the p-value. P-value equals. Okay. And then the question asks us, should we reject the null hypothesis? Our significance level is 5%. Our p-value is 1.24%. So The chances of something this unlikely happening is 1.24%. And before we started this analysis, we said anything less than 5% is too unlikely for us to believe, and we are going to reject the null hypothesis if the p-value is less than that. Selena? Is that right? I know, it gets confusing. P-value, critical values, less, more. We just need to get used to thinking this through in our head.
So the density value is 1.24 and that's less than 5% we rejected?
Yes. The chances of something this extreme happening, 1.24%. Our standard for how extreme before we say, no, we're not buying it, 5%. You give me a p-value less than 5%, I say, yeah, granted, that happens 1.24% of the time, but just so happens it happens this time when I'm paying you millions of dollars for this these supplies. No. I'm going to reject your assessment that you are giving me a mean value of 1,000, and I'm going to say that the alternative is true. Okay, let's move on. Let's look at number 46. We won't do it. I just want to talk it through. And then I've got some quick little type 1 and type 2 errors I want to go over with you. So I'll read it aloud, and we'll think about how we could calculate this. Suppose you're testing the following hypothesis. The mean is greater than 4,000 is the null hypothesis. Alternatively, the mean is less than 4,000. So this might be like, we used the tire strength example earlier. Suppose someone's telling us that their tires last 4,000 miles, and we're like, maybe not. So we're going to see if we get overwhelming evidence that it's less than 4,000. Sample size is 16. Sample mean is 3920. And the sample standard deviation is 200. Significance level is 1%. Assume the values in the population are normally distributed. Compute the sample test statistic t-stat. So what's the trick here? Like I said, we won't crank it out, but what's the difference here? We use the t. Oh, sorry. 339. Page 339, number 46. So the challenge here is that we use the t-stat because the population standard deviation is not known. So we use the t-distribution and we use the sample standard deviation. We calculate degrees of freedom. Sample size is 16, so degrees of freedom is how much? 15? Yes. The t-stats are going to be a little bit wider. And this is going to give you a chance to just punch into Excel how to work out the p-value. It'll give you the p-value if you just punch in some stuff in Excel. You have to play around with it. I forget exactly what it asks you. I just forget, but you'll practice. You have to punch in the number and the sample, and then the degrees of freedom, and then you have to put comma true because it's cumulative. I don't know exactly why they do that, but play with that and you'll be able to do that. Okay, last piece of information, and then we'll do one sample to illustrate it, are different types of errors. And you've heard me say this for the last 2.5 hours about the type of error you can make. All I'm going to do now is put it into a formalized process. Make various errors. One is a type 1 error. Type 1 error. That is rejecting a true null hypothesis. Rejecting a true null hypothesis. Okay, so this is the situation. Remember at the very beginning of class, which probably feels like 6 years ago at this point, but at the very beginning of class, we said on the extreme edges of the sampling distribution of the sample mean, this stuff can happen 5% of the time, 1% of the time. You know, if what the supplier says, if what the realtor says is true, we can have extreme results a certain percentage of the time. And we have to live with that. We have to live with the possibility of making that error, which is called a type 1 error, where we reject a true null hypothesis. And the significance level will measure the maximum probability of a type 1 error. Max probability. Max probability of a type 1 error. So, if our significance level is 5%, what is the max probability of making a type 1 error? 5%. 5%. Because we could, if it's a one-tail test or two-tail test, there's a 5% chance that we'll get something that extreme. And remember, we'll adjust the critical values based on a two-tail or one-tail test. So if we choose a significance level of 5%, that is the possibility we face of rejecting a true null and making a type 1 error. Type 2 error. Type 2 error is accepting a false null. Accepting a false null. So, in this case, we don't have overwhelming evidence to disprove the null. So we fail to reject it. Now, just because we don't have overwhelming evidence doesn't mean that it's true. So type 2 error is, well, we didn't have overwhelming evidence to reject it, but it wasn't true. We should have rejected it. Maybe we set the significance level at a too rigorous standard. Maybe it's just not as glaring of an error that we can find that overwhelming evidence. And unfortunately, there's no real way to know the probability of making a type 2 error. We just don't know. It could be anywhere from 0 to 100. I don't know exactly. We know the probability of making a type 1 error because we can quantify the chances of getting something that extreme. But we don't know the probability of making a type 2 error. All right. Yes.
So if you accept a null hypothesis, what needs to be the p-value?
We accept a null hypothesis. Well, it may have a p-value that's very high. It may have a p-value of 10%.
So there's no need to do it. P-value.
Oh no, you still do the p-value. Yeah, you'll still do the p-value. This is just, so suppose the p-value is 12% and you have a significance level of 10%. All right, in that case you would not reject, right? Because the p-value is higher than the significance level. But still, I mean, that only happens 12% of the time. You could walk into that realtor's office and say, I think you're wrong. there's a 12% chance, I could be wrong. Yeah. I really want to say that you're wrong because maybe the realtor is wrong. But you set the test up where you can't make that statement. All right, gosh, I'll be honest with you. I thought we would be out here sooner. I really did. But I hope this was helpful just going through it a little bit. I know it may feel confusing now. But just try to work through those examples again. Email me if you have questions. I'll look forward to seeing you next week. Thank you.